Hi everyone, my name is Lexiel Mendez Reyes, and we're going to be discussing the development of an automatic speech recognition model for non-standard speech. The research group is composed of Carlos Leiva Capote, Giovanni Benitez Rivera, Orlando Marrero Soto, Victor Vega Ward, and yours truly.
Hello everyone, my name is Victor Vega, and first off I'll give some background information about the current ongoing investigation that we're working on. The idea behind the project is focused on creating an automatic speech recognition system for dysarthric speech. This is a motor speech disorder and it's normally caused by medical conditions that affect the muscles used to produce speech. Regular speech recognition systems do not work as accurate for people with this speech disorder. This project is based on a research by Google called Euphoria, where they used a recurrent neural network transducer and trained it personalized for a person that has dysarthria. To define our problem statement, people that have dysarthric speech tend to also have a variety of muscle control issues that make it difficult for them to communicate with humans and with computers, since writing and/or sign language requires accurate motor skill movements. Since current ASR systems do not take into consideration the characteristics of dysarthric pronunciation, the prediction they return aren't as accurate as with standard speech. Addressing this issue by developing an SAR model that is capable of understanding dysarthric speech would allow these people to take advantage of voice-activated command systems, speech transcription, thus allowing them to communicate with others more efficiently.
This issue can be solved by training models to interpret the characteristics of cathartic speech and use them as features to give accurate predictions. A method that can be used to train these models is through transfer learning from models that are already trained. Among these methods, there is knowledge distillation, where a student model is optimized to return similar values of a pre-trained model, known as the teacher. This method has been tested via cross-model knowledge distillation, where the teacher model is an encoder from a text-to-speech model, and the student is an encoder that will interpret the dysarthric speech audio as the standard text encoder. The outcome was a model capable of translating dysarthric speech into standard speech.
We were able to finish three crucial tasks. The first one being the development of the data generators. They work by taking the data from the LJ speech dataset for standard speech and the UA speech dataset for dysarthric speech. The first pre-processing that is applied is a fast Fourier transform that will turn the wave data into a frequency data, thus giving us the MEL spectrogram that we're gonna use to train the model. These MEL spectrograms are then fed into the model through batches. We were also able to develop the model architecture that we're going to be training, that is known as a bidirectional long short-term memory autoencoder, composed of two parts, the first one being the encoder that will create a feature representation of the MEL spectrogram through a series of convolutions. This feature embedding is then fed to the decoder that uses a series of bidirectional convolutional long short-term memory to classify the audio. And finally, we were able to develop the training environment that we're going to be using. The knowledge distillation environment is the method used to train the dysarthric model through transfer learning. It receives two inputs of data, which are the dysarthric and standard version of the same label, and pass them through two encoders. The student model will be optimized to return a similar embedding than the one returned by the teacher model, thus optimizing the encoder to interpret dysarthric speech as if it were standard speech.
As for the current status of the project, we encountered some issues since last semester. We were only able to build the models, the data generators, and the training environments. Due to the complexity of these tasks, they took longer than anticipated to develop, and we were unable to train the model. The other issue being that most of the members from last semester were unable to continue participating due to academic weight. For this reason, we had to put the research on hold until we had enough members to continue.
To address the issue of the lack of members, the decision was made to recruit new students and train them in the fundamental machine learning concepts. The members recruited were ones with interest in the areas of artificial intelligence that possessed prior knowledge of data structures and linear algebra. The training process consisted of studying machine learning concepts through the Stanford Machine Learning course. Through this course, we learned the mathematical theory behind linear regression, logistic regression, and neural networks. And throughout the semester, we tested our understanding of each of these concepts by implementing and training each model utilizing Python and NumPy libraries.
As for our future work, the knowledge distillation is the next milestone of the project, since this will give us a model that we can test for dysaorthic speech. After the model is trained, we will be able to obtain test results and validate the accuracy of the model and the method used for training. If the model returns good results, we will try the aspect of personalized models by fine-tuning the model using data from a single person.